All right, so this is the video for section 4.4 for business calculus. And what we're going to see here is two applications to economics, which are relative rates, and elasticity of demand. All right, so the derivative of a function gives its rate of change. We've learned that all the way through. So for example, if f of t is the cost of a pair of shoes at time t, then f prime of t is the rate of change of cost in dollars per year. Meaning, f prime of 3 means that the price of shoes is increasing at a rate of $3 per year. Well, similarly, if g of t is the price of a new automobile at time t years, then g prime equal to 300 would mean that automobile prices are increasing at a rate of 300 per year. So does this mean that car prices are rising 100 times as fast as shoe prices? And in absolute terms, yes. However, this does not take into account the enormous price difference between automobiles and shoes. So what we're going to be able to do is talk about relative rates of change, which will take into account that difference in price and help us compare the two. So what is a relative rate of change? Well, relative rates of change is if f of t is the price of an item at time t, then the rate of change is f prime of t. And the relative rate of change is f prime of t divided by f of t, or the derivative divided by the function. Sometimes we will call f prime of x the absolute rate of change, just so we can distinguish it from that relative rate of change that we're now learning. So relative rates, where they're handy, they're more meaningful than absolute rates. So for example, it's easier to grasp the fact that the gross domestic product is growing at the relative rate of 3% a year than it is growing at the absolute rate of 4 billion per year. Okay, if you didn't know what that total was, that 4 billion really wouldn't matter to you as much as seeing it's growing at 3% per year. All right, so the expression f prime of x divided by f of x is the derivative of the natural logarithm of f of x. Okay, so recall that from the last section. Derivative of x of ln of f of x is f prime over f of x. So this provides us with an alternative expression for the relative rate of change in terms of logarithm. So that relative rate of change of f of t is either the derivative of the logarithm of the function or f prime over f of t. And it may not seem like there's much of a difference there, or it's like a does statement, but what we're going to see is we have two options. We can take the derivative of the function and then divide by the original function and get an answer. Or we can take the ln of our original function first and use the properties of logarithms to expand it and simplify it, and then take a derivative. And we'll see a much easier problem show up, which is going to be nice. So we use the variable t since it often stands for time. Both formulas in the box give the same result. And the middle expression is sometimes called the logarithmic derivative, since it's found by first taking the logarithm and then the derivative. So this middle one is what they're calling the logarithmic derivative. The relative rate of change, being a ratio or a percent, does not depend on the units of the function. Therefore, relative rates can be compared between different products and even between different nations. This is in contrast to absolute rates of change, or those just the plain derivative, which do depend on units. So for example, dollars per year. So let's try one. If the gross domestic product t years from now is predicted to be g of t equal to 8.2 e to the square root of t trillion dollars, we need to find the relative rate of change 25 years from now. We're going to show, or I'm going to show it both ways, taking the logarithm first and then the derivative, or just doing f prime over f. Okay, so the first one I'm going to try, I'm going to write this one in blue, is taking the logarithm of g of t, which is the ln of 8.2 e to the square root of t. What we're going to do is we're going to use the properties of logarithms to expand this, giving us ln of 8.2 plus ln of e to the square root of t. Okay, remember, if there's a product inside a logarithm, we can split it up as addition. And what we see here, if you remember, the square root of t can come out front, and ln of e is equal to 1. So what we have is the ln of g of t is equal to the ln of 8.2 plus the square root of t. T, not 2, sorry. And now we can take the derivative. So if I take the derivative of ln of g of t, both sides, we end up with the ln of 8.2 is just a constant, and remember the derivative of a constant is 0. And then the square root of t, if you recall, is t to the 1/2. So we take the derivative there, we have 1/2 t to the negative 1/2. Through simplifying, we get that our derivative is 1/2 t to the negative 1/2. Now we want to figure out what that relative rate of change is 25 years from now. Okay, so there's our t value, that 25. And if we plug that in, so plugging this into the derivative, I have 1/2 times 1 over the square root of 25, which is 1/2 times 1 over 5, or 1/10. Meaning, or 0.10, this means that in 25 years, that gross domestic product will be increasing at a relative rate of 10% per year. Okay, so it's going up, it's increasing 10% per year. Okay, that's one way to do it. Take the logarithm, use the properties of logarithms to expand, and then take the derivative. The second way that you can tackle this, and I'm going to write this in pink, is just to use that formula f prime over f. Okay, so we're going to take the derivative of the g of t. So g of t is 8.2 e to the square root of t. If we take that derivative, g prime of t, we end up with 8.2 e to the square root of t times the derivative of the inside function, or the derivative of the exponent, sorry, not inside function. So we have 1/2 t to the negative 1/2. All right? So when we put this together, we have 8.2 e to the square root of t times 1/2 t to the negative 1/2 all over 8.2 e to the square root of t. We see that our 8.2 e to the square root of t cancels out, and we get 1/2 t to the negative 1/2. Right? So we end up with the exact same thing. And again, at that relative rate, or at that time frame of t equal to 25, it would be the exact same thing. 1/2 times 25 to the negative 1/2 would be 1/10, or 0.10. And that growth rate is 10%, just like we found before. It really doesn't matter which way you do it. Depending on the function, I prefer taking the logarithm first just to simplify what I can. But it truly doesn't matter. Both ways will get you the exact same answer. All right, let's keep going. All right, so the next thing we're talking about in this section is elasticity of demand. And farmers are aware of the paradox that an abundant harvest usually brings lower total revenue than a poor harvest. The reason is simply that the larger quantities in an abundant harvest result in lower prices, which in turn cause increased demand, but the demand does not increase enough to compensate for the lower prices. Remember that revenue is price times quantity, and when one of these quantities rise, the other falls. Okay, so the question is whether the rise in one is enough to compensate for the fall in the other. So for example, if a 1% price decrease brings a 2% quantity increase, revenue will rise. But if the 1% price decrease only brings in 0.5% quantity increase, revenue is going to fall. Okay, for multiplying those together. So the concept of elasticity of demand was invented to analyze such problems. So roughly speaking, we can think of elasticity as the percentage change in demand divided by the percentage change in price. Okay? So your elasticity is your percentage change in demand divided by your percentage change in price. So brief examples. If a 1% change in price brings a 2% change in demand, the elasticity is 2. If a 1% change in price brings only a 0.5% change in demand, your elasticity is 1/2. Well, what does this E value mean? Let's look at this next slide. We classify demand as elastic or inelastic depending on whether the elasticity is greater than 1 or less than 1. Okay, so if your demand is greater than 1, it's elastic. Less than 1 is inelastic. And when E is equal to 1, it's unit elastic. Okay, so in the example above, E equal to 2, demand was elastic. But in the second one, E was equal to 1/2, so it's inelastic. And intuitively, we can think of elasticity of demand as measuring how responsive demand is to price changes. Okay, so elastic means responsive, and inelastic means it's going to be unresponsive. That is, for elastic demand, a price cut will bring a large increase in demand, so total revenue will rise, which is what we want. But if it's inelastic, a price cut will only bring a slight increase in demand, so revenue will fall. All right, we're going to finish up this next section in the next video.